Hello, everyone. So last time we looked at the concept of derivatives and we looked at the definition and some examples. Derivatives. So we define, f prime of A as the limit f of x minus f of A over x minus A, x approaches to A. And this one, we could also write it as limit f of A plus h minus f of A over h approaches to 0. And we saw that f prime of A represents the slope of tangent line at x equals A. Right? And we use this fact to find the connection between the graph of a function and the graph of its derivative. So if you remember the last example we did last time, we had some graphs and the question was asking us to match the graph of the function with the graph of the derivative of that function. So we use this fact that, if slope of tangent line slope of tangent line to the graph is positive. Let's say, for example, if the original graph looks like this, that means slope of tangent line is positive. And if the slope of tangent line is positive, means derivative is positive, and therefore the graph of derivative has to be above x-axis. So if the graph looks like this, the graph of a derivative has to be above x-axis. But if the slope of tangent line is negative like this, or even like even if the original graph is above x-axis, as long as the slope of tangent line is negative, that means the derivative of the function will be below x-axis because it will be negative. Okay, so let's also look at some another notation for derivatives. Important notation for derivatives. So this one is called the Leibniz notation. We saw that, the derivative at some point A, let's say, is a limit, basically limit delta y over delta x as delta x approaches to 0. Right? So this one, which was same as limit, basically f of x minus f of a over x minus a, x approaches to a. Right? So x minus a is delta x, f of x minus f of y is delta y, or change in y. And as x approaches to a, delta x, which is the difference between x and a, approaches to 0. Right? So now the notation that we use for this one, so this is denoted by dy to dx. So dy to dx means, or represents this limit delta y over delta x as delta x approaches to 0. So dy to dx defined as limit delta y over delta x as delta x approaches to 0. So it's called Leibniz notation for derivatives. Okay, so dy to dx is another notation for f prime of x. So in other words, if y is equal to f of x, then dy to dx is defined as f prime of x. So I want to also say here about, it's just a notation. I want to say about when the concept of, derivative as a function. So far we looked at derivative at a fixed point, derivative of a function at a fixed point. But what about if we want to look at derivative as a function itself? So derivative as a function. So let y equals f of x be a function with domain df so f of x a function with domain df, then f prime of x, y equals f prime of x is defined as a function with, okay, see, I want to introduce a new function. When I want to introduce a new function, I have to introduce its domain and also its formula. So for the original function f of x, I know the formula and I know the domain. For the new function f prime of x, I need to introduce the domain and the formula. So first, let's introduce the domain. What should I consider as the domain of f prime of x? So with the domain of set of all points in df such that y equals f of x is differentiable at those points, furthermore, f prime of x at such points is defined as follows. So f prime of x is equal to limit f of x plus h minus f of x over h as h approaches to 0. Okay, so here f prime of x, so still same definition as before. The only difference is that previously we fixed some x value as a. Let's say f prime of a, we defined it as limit f of a plus h minus f of a over h. But here f prime of x is, we're looking at it as a function, which at point x, at some arbitrary point x, is defined as limit f of x plus h minus f of x over h as h approaches to 0. And the domain of this function is same as the domain of the original function f, except the points where the function is not differentiable. Because if the function is not differentiable, that means this limit here does not exist. And therefore, f prime of that point cannot be defined, right? So if f prime of a number cannot be defined, that means that number cannot be in the domain of f prime. So when you want to define the domain of a function, of course, we have to exclude the points where the function is undefined at those points. So let's look at an example. So this is the before looking at the example, let me first look at the tell you about the concept of second derivative. So higher derivatives, higher derivatives. All right, so let's look at the function. Let y equals f of x be a function be a, let's say, differentiable function and let's say let y equals f prime of x be the derivative function as defined above, then f double prime of a called the second derivative of f at x equals a is defined as follows. So second derivative of f at a, f double prime of a, is defined as limit f prime of a plus h minus f prime of a divided by h as h approaches to 0. So f prime itself is a function. So it has a formula, it has a domain. So we can find f prime of a plus h. How would you find f prime of a plus h? So that means in the formula for f prime of x, you need to replace x by a plus h. Then you find f prime of a plus h. And then minus f prime of a, that would be an expression. Find the limit of that expression over h as h approaches to 0. And then you will have an answer. So that will be called the second derivative of f at x equals a, or f double prime of a. Okay, of course, if the limit exists. If this limit exists, and if the limit does not exist, we say that f double prime of a does not exist, or the second derivative does not exist at x equals a, or sometimes we say or f is not twice differentiable at x equals a. And so this is the second derivative at the fixed point. Similarly, we can, like previously, we also first defined the first derivative at a fixed point. Then we define the first derivative at an arbitrary point x, or as a function, basically, right? So we can do the same thing here, and we can define the second derivative as a function again. So similar to above. We can define f double prime of x as a function. So f double prime of x is defined as limit f prime of x plus h minus f prime of x over h as h approaches to 0. And domain of f double prime with domain of f double prime is same as domain of f prime, except or minus the set of points minus the, let me say it this way, domain of f double prime. I don't have space here. is defined as domain of f prime except the set of points x such that x is in domain of f prime and f double prime of x does not exist. So just a trivial restriction that of course domain of f double prime, if f double prime is undefined at some point, then we cannot include that point as a part of domain of f double prime, right? So from the domain of f prime, we have to exclude the points where f double prime does not exist at those points. Okay, so this is the f double prime of x as a function. And Leibniz, we also have a Leibniz notation for f double prime. Leibniz notation is that, if you have y equals f of x, then second derivative of f respect to x is denoted by d squared y over dx squared. Okay, so please pay attention to this notation. For the first one, the power is above d, and then in the denominator is above x. D squared y over dx squared. So this one is defined as f double prime of x. So this notion, this notion can be generalized to higher derivatives as well. So for example, f triple x is defined as f third derivative, basically. F third derivative is defined as limit f double prime of x plus h minus f double prime of x over h as h approaches to 0. Or fourth derivative, at x is limit third derivative x plus h minus the third derivative x over h approaches to 0. And so on. Okay, you may ask, why or how is that useful to define, second derivative, third derivative, and so on. So there are many applications, again, similar to the first derivative that has many applications. Second derivative also has applications. So for example, we will see later that second derivative determines concavity of a function. Is it concave upward, like for example, this function? Concave upward like this function, or concave downward like this function. So this one is determined by second derivative. So we will see that later. Okay, so first derivative, we saw it's the slope of tangent line. Second derivative determines concavity of the function. It also has other applications. We'll get into the applications later. But for now, let's stick to the definition and let's stick to some examples. So let's look at an example. Let's say f of x equals, for example, let's say 2x cubed minus x squared plus 1, and use the limit definition of derivatives to evaluate, let's say, f double prime of 4. So what is f double prime of 4? So we know, so the solution. Let's look at the solution. So first we need the function f prime of x, because we know f double prime is the derivative of f prime. So first, we will find f prime of x, right? And so we know that f prime of x is equal to limit, remember the limit definition of f prime, limit f of x plus h minus f of x over h as h approaches to 0. And then we have the formula for f of x. F of x is here. So for f of x plus h, we have to replace x by x plus h. So limit 2 times x plus h cubed minus x plus h squared plus 1. This is f of x plus h, and then minus f of x. So minus 2x cubed minus x squared plus 1 divided by h as h approaches to 0, right? So the first 3 terms, you look at this fraction is f of x plus h minus f of x over h. So the first 3 terms here are for f of x plus h, and the next 3 terms are for f of x. And then this is limit 2 times x cubed plus 3x squared h, 3x h squared h cubed. I have enough space here, maybe I can write it here. Limit 2 times x cubed, 3x squared h, 3x h squared h cubed minus x squared plus 2x h squared. Now 1 and minus 1, they cancel. There's 1 here, there's minus 1 here, they cancel. Minus 2x cubed plus x squared divided by h. H approaches to 0. And then this is limit 2x cubed plus 6x squared h, 6x h squared, 2h cubed minus x squared minus 2xh minus h squared minus 2x cubed plus x squared divided by h. Now if we simplify this further, 2x cubed and minus 2x cubed, they cancel. X squared and minus x squared, they cancel. So limit, I can take h out, right? So see, this one is already canceled with this. And this one canceled with this. So we are left with h times 6x squared plus 6xh, 2h squared, and then minus 2, 2h squared minus 2x, and then minus h divided by h. H approaches to 0. Now h cancels with h. And then this is 6x squared minus 2x. Right, so as h approaches to 0, the terms that include h will be 0, right? So 6xh, because h approaches to 0, the limit will be 0. This one limit will be 0. This one limit will be 0. So we will be left with 6x squared from this term and minus 2x from this term. So 6x squared minus 2x. So we concluded that if f of x equals 2x cubed minus x squared plus 1, then f prime of x is 6x squared minus 2x. Okay, now we need next, we need f double prime of 4. So f double prime of 4, we saw that its limit f prime of x plus h minus f prime of x, f prime of say 4 plus h, because x is 4 here, right? So 4 plus h minus f prime of 4 divided by h approaches to 0. Now this is limit as h approaches to 0 of what function? So this function here, 6x squared minus 2x, so 6 times 4 plus h squared minus 2 times 4 plus h minus, then 6 times 4 squared minus 2 times 4 divided by h. Now if we simplify this, 6 times 4 squared plus 8h plus h squared minus 8 minus 2h minus 6 times 4 squared plus 2 times 4, or 8. Divided by h approaches to 0. 6 times 4 squared and 6 times 4 squared, they cancel. So then we will be left with 48h. And then minus 2h is 46h. And then we'll have 6h squared. And then divided by h. And then this is limit h times 46 plus 6h divided by h approaches to 0. And the answer is 46, because h cancels with h, and then 6h, the limit of 6h will be 0 as h approaches to 0, and then we will be left with 46. I can add another part for this question as an exercise, as a part B exercise. Find a formula for f double prime of x. So in part A, we found f double prime of 4, but you can similarly find f double prime of x for any x. The only difference is that the formula that you have to use, of course, will be like f prime of x plus h minus f prime of x over h, the limit as h approaches to 0. Now another example, let's say let f of x equals absolute value x. Find f prime of x and its domain. Okay, so remember I promised you to do an example where it includes the domain of f prime or domain of f double prime, so that we can see how we can find the domain of these functions. So what is domain of f prime? So domain of f prime is equal to a domain of f minus the set of points in domain of f, such that f of x is or let's say points A, let's say, such that f of x is not differentiable at x equals A. Okay, so of course, if the function is not differentiable at a point, we have to exclude that point for the domain of f prime. So what is domain of f here? Here, domain of f, domain of absolute value x is all real numbers or minus infinity to infinity, right? Absolute value x is defined at every point, so domain is all real numbers. But is there any point where f of x is not differentiable? Furthermore, f of x equals absolute value x is not differentiable at x equals 0, right? Because limit absolute value x minus 0 over x as x approaches to 0 does not exist. And f of x equals absolute value x is differentiable at x equals a for every real number a not equal to 0. So at 0, the function is not differentiable, but at every other point it is differentiable. Right? So what is the domain of f prime? So domain of f prime is equal to all real numbers except 0, right? We said domain of f prime is domain of f except the points where f is not differentiable. Well, the only point where f is not differentiable is x equals 0. So domain of f prime is all real numbers except 0. And what about the formula for f prime of x? Formula for f prime of x. Now that depends on the formula for f of x. So recall that f of x is equal to absolute value x, which is equal to x itself if x is bigger than or equal to 0, and minus x if x less than 0, right? So what can we say about f prime of x? So thus, if a is bigger than 0, then we can say that f prime of a is equal to limit f of a plus h minus f of a over h as h approaches to 0. Now, if a is positive, then we have to use the first formula here, which is x itself. So then this is limit a plus h minus a over h. H approaches to 0. A cancels with a, and h over h is 1. And if a is less than 0, f prime of a is equal to limit f of a plus h minus f of a over h. H approaches to 0, then this is equal to limit so a plus h. If a is less than 0, we have to use the second formula, which is minus x. So minus bracket a plus h, we have to replace x by a plus h. So minus bracket a plus h minus f of a. F of a will be minus a divided by h. H approaches to 0. Now minus a plus a, they cancel. And then we are left with limit minus a plus minus a minus h plus a over h. H approaches to 0. The answer is minus 1. So we can say that f prime of x is equal to 1 if x is bigger than 0, and minus 1 if x is less than 0, right? Minus 1 here if a is less than 0, and we saw that if x bigger than 0 or a bigger than 0, f prime of a is 1. So f prime of x is 1 if x bigger than 0, minus 1 if x less than 0. And domain of f prime is how much? Domain of f prime will be r minus 0, as we said, which is same as minus infinity to 0 union 0 to infinity. Okay, so domain of f is all real numbers. Domain of f prime is all real numbers except 0. For x bigger than 0, f prime is 1. For x less than 0, f prime is minus 1. Let's look at another example. Consider f of x equals x times sine 1 over x if x not equal to 0 and 0 if x equals 0. So part A is f continuous at x equals a. Part B is f differentiable at x equals a. So solution for part A, the answer is yes, it's a continuous function. This function f is continuous function. Why is it continuous? Because we saw that limit x times sine 1 over x as x approaches to 0. This is 0. So this one we proved before using squeezing theorem. Remember, we proved that this limit is 0 using squeezing theorem. And this is limit f of x as x approaches to 0, which is 0. And this 0 is same as f of 0. So we can say limit f of x as x approaches to 0 is equal to f of 0. And that means f of x is continuous at x equals 0. Okay. And is it differentiable? Oh, sorry, I said x equals a, I meant 0. My RA is 0 here. Is f differentiable at 0? How can we answer? So we need to look at limit f of x minus f of 0 over x minus 0 as x approaches to 0. So then this is how much? This is limit x times sine 1 over x minus 0 over x as x approaches to 0. And then this is how much? This is limit sine 1 over x as x approaches to 0. And this limit we saw that does not exist. Again, we have seen this in the past. We have seen this before. That limit sine 1 over x as x approaches to 0, which is same as limit sine t, basically, as t approaches to infinity or minus infinity. We saw that that limit or those limits do not exist. So this limit does not exist means f of x is not differentiable at x equals 0. Okay.